Constructive interference in physics, a harmonious dance of waves. Introduction. Waves are everywhere, from the ripples on a pond to the light that illuminates our world. These oscillations, whether in water, sound, or electromagnetic fields, are fundamental to the fabric of our universe. Among the many fascinating phenomena in wave physics, interference stands out as one of the most intriguing. Interference occurs when two or more waves meet, resulting in a new wave pattern. This essay will explore the concept of constructive interference, a specific type of interference that leads to the amplification of waves, creating a stronger and more pronounced resultant wave. Explanation. To understand constructive interference, it's essential first to grasp the basics of wave behavior. Waves are characterized by their amplitude, wavelength, frequency, and phase. The amplitude represents the wave's height or intensity. The wavelength is the distance between successive wave crests, the frequency denotes how often the wave cycles occur, and the phase indicates the wave's position at a given point in time. Interference occurs when two or more waves overlap in space and time. When the crests, the highest points, and troughs, the lowest points of these waves align perfectly, their effects combine. This alignment can lead to two types of interference, constructive and destructive. Constructive interference happens when the crests of one wave align with the crests of another, and the troughs align with the troughs. In this case, the waves reinforce each other, leading to a wave with a greater amplitude than the individual waves. Imagine two pebbles dropped into a calm pond. Each pebble creates circular waves that propagate outward. When these waves meet, if their crests coincide, the resulting wave is higher than the waves from each pebble. This is constructive interference in action. The principle applies across different types of waves, including sound, light, and even quantum mechanical probability waves. A classic example of constructive interference is seen in the double-slit experiment, a foundational demonstration in wave physics. When light passes through two closely spaced slits, the waves emanating from each slit interfere with each other. Where the crests from both slits meet, the light intensity is greater, resulting in bright bands on a screen. These bright bands are a direct result of constructive interference. Constructive interference is not just a theoretical concept, it has practical applications in various fields. In telecommunications, for instance, antennas are designed to use constructive interference to amplify signals, improving reception and clarity. Similarly, in acoustics, concert halls are constructed to take advantage of constructive interference, enhancing sound quality for the audience. The phenomenon also plays a role in the design of noise-cancelling headphones, which use destructive interference to reduce unwanted sounds, but rely on understanding constructive interference to ensure that the desired sounds are heard clearly. What are the counter-arguments? While constructive interference is a widely accepted and well-understood phenomenon in physics, some counter-arguments or points of consideration can arise, particularly when discussing its applications or limitations. Here are some of these counter-arguments. 1. Dependence on ideal conditions. 1. Argument. Constructive interference relies on the precise alignment of wave crests and troughs. 1. In real-world scenarios, achieving and maintaining the exact conditions needed for constructive interference can be challenging. 2. Counter-argument. Environmental factors such as medium inhomogeneities, wave dispersion, or interference from other sources can prevent perfect alignment, leading to partial or no constructive interference. 2. For example, in telecommunications, signal degradation over long distances can reduce the effectiveness of constructive interference. 2. Energy considerations. 1. Argument. Constructive interference might seem to suggest a creation of energy because the resultant wave has a higher amplitude than the individual waves. 2. Counter-argument. This might be interpreted as a violation of the conservation of energy principle. 2. However, the total energy in a system of interfering waves remains constant. It is merely redistributed. 2. The increased amplitude in areas of constructive interference is balanced by areas of destructive interference where the amplitude is reduced. 3. Interference in complex systems. 1. Argument. In complex systems where multiple waves interact, the predictability and control of constructive interference become increasingly difficult. 2. Counter-argument. In such systems, interference patterns can be chaotic and unpredictable, making it challenging to harness constructive interference effectively. 2. For example, in acoustic environments with multiple sound sources, constructive interference might enhance some frequencies while simultaneously creating undesirable noise in others. 4. Practical limitations in technology. 1. Argument. While constructive interference is theoretically beneficial in technologies like antennas or acoustics, its practical implementation can be limited. 2. Counter-argument. The design of devices to harness constructive interference often requires precise engineering and calibration. 2. Small deviations can lead to inefficiencies or even unintended destructive interference. 2. For instance, in noise-cancelling headphones, the exact timing and phase alignment of sound waves are critical, and any misalignment can reduce the effectiveness of noise cancellation. 5. Ethical and environmental concerns. 1. Argument. The use of constructive interference in certain technologies could have unintended environmental or health impacts. 2. Counter-argument. High-intensity electromagnetic waves, for example, might enhance communication signals through constructive interference, but could also raise concerns about increased exposure to radiation, leading to potential health risks. 2. Similarly, the amplification of sound in certain environments could contribute to noise pollution. 6. Misinterpretation of wave behavior. 1. Argument. Constructive interference can be misunderstood, especially in non-physical wave contexts, leading to incorrect assumptions about how waves interact. 2. Counter-argument. In quantum mechanics, for instance, constructive interference of probability waves can lead to misconceptions about the nature of particles and their behavior. 2. This highlights the importance of a clear understanding of the context in which constructive interference is applied. Conclusion. Constructive interference is a powerful and pervasive phenomenon that highlights the beauty of wave interactions. By combining wave crests and troughs in perfect harmony, it amplifies the energy and effects of the individual waves, creating something greater than the sum of its parts. This principle not only deepens our understanding of the natural world, but also drives innovations in technology and engineering. As we continue to explore the wave-like nature of our universe, constructive interference will remain a cornerstone concept, demonstrating the remarkable ways in which waves can shape and enhance our reality. Please don't forget to like, share and subscribe to see more videos like this. Thank you.